Remember that iconic scene from the movie Interstellar, where Cooper plunges into a black hole and suddenly finds himself inside a 5-dimensional library, watching moments from his daughter's life like pages in a book. It made us all wonder, could something like that ever be real? Today, we're not just talking about Hollywood's take on time travel. We're diving into the real science behind wormholes and closed time-like curves, the cosmic shortcuts that just might make skipping through time more than science fiction. From Einstein's theories to cutting-edge physics, we'll explore whether the universe has secret doors hidden in the fabric of space-time, waiting for us to step through. Buckle up, this journey's about to bend more than just your mind. Einstein once said that the distinction between past, present, and future is only an illusion, though a stubbornly persistent one. And when it comes to time travel, his theory of relativity is the key to unraveling that illusion. According to Einstein, space and time aren't separate, they're woven together into a flexible fabric called spacetime, which can bend and stretch under the influence of gravity. The stronger the gravity, the slower time moves. We've actually measured this effect. Atomic clocks on airplanes tick slightly faster than those on the ground, proving time isn't fixed but fluid. Now, if gravity can slow time down, could it theoretically twist spacetime enough to create a bridge between different moments? That's where things get mind-bending. Relativity doesn't just allow for time dilation. It also opens the door to more exotic possibilities, like warping spacetime so drastically that a path back to the past could exist. Think of it like this: if spacetime is a sheet of paper, a massive object like a black hole bends it so much that the edges might touch, creating a shortcut between 2 points in time. The math supports it, but the universe has rules. To bend time without breaking physics, we'd need something extraordinary, like wormholes or cosmic strings, structures so strange they sound like science fiction, yet they emerge from real equations scribbled by physicists. So while we can't hop into a DeLorean just yet, the universe may have left the door slightly ajar, if only we can find the key. So if bending spacetime is the first step toward time travel, wormholes might just be the ultimate cheat code. Picture the universe as a crumpled piece of paper. 2 distant points could suddenly touch if you fold it just right. That's the basic idea behind wormholes, shortcuts through spacetime, like cosmic tunnels linking separate moments or places in an instant. First dreamed up by Einstein and physicist Nathan Rosen back in the 1930s, these theoretical passages emerged straight from the equations of general relativity. But here's the catch: while the math allows them, nature throws up some serious roadblocks. For a wormhole to stay open, let alone be traversable, you'd need something called exotic matter. Not just any material, but stuff with negative energy which defies gravity instead of obeying it. Imagine trying to prop open a tunnel with anti-gravity springs. It sounds absurd, but quantum physics hints that tiny amounts of negative energy might actually exist. Even then, the stability of a human-sized wormhole is another headache. One wrong move, and the tunnel could collapse faster than you can say. Time paradox. Yet despite the hurdles, the sheer possibility keeps scientists intrigued. After all, if wormholes exist, even fleetingly, they'd rewrite the rules of not just space travel but time itself. One could step in on a Tuesday and emerge somewhere else on the previous Monday, and that's where the real fun and the real puzzles begin. Not all wormholes are created equal. Some might be cosmic dead ends, while others could hold the ticket to time travel. The simplest kind, predicted by Einstein's equations, are called Schwarzschild wormholes. Picture a black hole's entrance connecting to a white hole's exit, like a one-way tunnel where matter gets sucked in but never comes out the other side. These are non-traversable, meaning anything entering would be crushed by infinite gravity long before reaching the other side. But then there's the holy grail, traversable wormholes. Popularized by physicist Kip Thorne in the 1980s, these theoretical passages could, if they exist, allow safe travel through space-time. For that to work, their throats would need to stay wide and stable, propped open by exotic matter or some undiscovered cosmic glue. The wildest twist: if one end of a traversable wormhole moved at near light speed while the other stayed still, time dilation would kick in. You could step in on the moving side and emerge on the stationary side, but in the past. It's like taking an elevator between timelines. Of course, this raises thorny questions. Would such a loop create paradoxes, like going back to prevent your own birth? Quantum physics offers fuzzy answers, suggesting parallel timelines might sidestep the problem. While we're light years from building one, the fact that nature might allow such structures at all keeps the dream alive. After all, if space-time can bend, who's to say it can't fold into a bridge across time itself? The idea of constructing a wormhole might sound like something ripped straight from a sci-fi blueprint, but believe it or not, physicists have sketched out some theoretical blueprints of their own. So how would we even begin to build a tunnel through space-time? First, you'd need a way to pry open the fabric of the universe, which is where exotic matter comes in. Unlike the ordinary stuff around us, exotic matter doesn't just bend to gravity's will, it pushes back. Picture trying to hold open a doorway with repelling magnets instead of hinges. That's the kind of negative energy density you'd need to counteract the crushing weight of a wormhole's walls. Quantum mechanics hints that this isn't entirely fantasy. Virtual particles flicker in and out of existence with negative energy all the time in empty space. The catch: scaling that up to stabilize a human-sized wormhole would require amounts of exotic matter we can't even imagine producing yet. Another wild card. The energy required might be astronomical, literally. Some calculations suggest you'd need the equivalent of a star's worth of mass converted into negative energy just to keep the tunnel open long enough to step through. And even if we cracked that, there's the problem of control. A stable wormhole isn't just about propping it open, it's about fine-tuning the entrance and exit points so you don't accidentally emerge inside a black hole or a billion years in the past. The equations show it's possible, but the engineering, that's a puzzle even the brightest minds are still piecing together. For now, wormholes remain a dazzling what if scribbled in the margins of physics. But the fact that we can even theorize about building them is a testament to how strangely flexible our universe might really be. Hollywood has always had a love affair with wormholes, bending them to fit stories in ways that thrill audiences, even if they sometimes stretch the science beyond recognition. Take Interstellar, for example, where a wormhole near Saturn becomes humanity's gateway to survival. The film consulted physicist Kip Thorne to get the visuals right, depicting the wormhole as a shimmering sphere warping starlight around it. That part surprisingly close to real physics, but the idea of navigating one with a spacecraft, that's where fiction takes liberties. Real wormholes would likely tear anything apart with tidal forces before it even reached the center. Then there's Stargate, where ancient alien tech creates stable portals across galaxies. While the concept of an instant doorway is fun, the show sidesteps the pesky need for exotic matter entirely. Books like Contact by Carl Sagan take a slightly more grounded approach, treating wormholes as engineered constructs rather than natural phenomena. Even Thor's Bifrost Bridge borrows wormhole-like logic, blending Norse mythology with sci-fi flair. What's fascinating is how these stories all tap into the same human longing to leap across the cosmos in a single step. The truth, though, is far stranger than fiction. Real wormholes wouldn't glow ominously or hum with energy. They'd be invisible, lurking in the math until someone or something figured out how to pry them open. So while Hollywood gives us spectacle, science whispers something even more compelling. The universe might already have these tunnels woven into its fabric. We just haven't found the map yet. If wormholes are cosmic shortcuts through space-time, then closed time-like curves are the universe's way of tying time into a knot. These mind-bending structures, often just called CTCs, are paths that loop back on themselves, allowing an object or even a person to travel forward in time only to return to their own past. Unlike wormholes, which act as bridges between distant points, CTCs are more like a record player's needle stuck in a groove, tracing the same moment over and over. The idea might sound like pure fantasy, but it emerges straight from Einstein's equations. In regions of extreme gravity, say near a spinning black hole, space-time could twist so violently that time itself folds into a circle. Picture walking in a straight line around the Earth. Eventually, you'd end up where you started. A CTC does the same thing, but with time instead of space. Now, here's where it gets even stranger. While wormholes require exotic matter to stay open, CTCs might exist naturally, at least on paper. The catch: they'd likely be hidden in the most chaotic corners of the universe, where gravity warps reality beyond recognition. Some theories even suggest that quantum particles could traverse these loops without causing paradoxes, as if nature has its own set of loopholes. Of course, no one's found proof of CTCs yet, but the fact that they're mathematically possible hints that time, far from being a one-way street, might have hidden roundabouts we've yet to discover. Einstein's equations are like a cosmic puzzle box. They contain solutions so strange they defy everyday intuition, and closed time-like curves are one of their most bizarre offerings. Take the Gödel metric, a solution cooked up by mathematician Kurt Gödel in the 1940s. It describes a universe spinning so uniformly that if you traveled far enough in a straight line, you'd end up right back where you started, not just in space but in time. In this twisted cosmic ballet, time itself becomes a loop with no beginning or end. Then there's the Tipler cylinder, a thought experiment dreamed up by physicist Frank Tipler. Imagine a cylinder made of impossibly dense material, spinning at nearly the speed of light. According to relativity, its rotation would drag space-time around it like a whirlpool, twisting time into a helical path. Circle the cylinder enough times, and you'd arrive back at a moment in your own past, like a cosmic Möbius strip. These aren't just wild guesses, they're mathematically rigorous predictions straight from Einstein's playbook. But here's the twist: while the numbers check out, nature might have built in safeguards. Quantum effects or energy conditions could prevent CTCs from forming in the real universe, or at least make them vanishingly rare. Still, the mere fact that these solutions exist tells us something profound. Time, as we know it, might not be the rigid, one-way river we assume. Under extreme conditions, it could bend, twist, or even tie itself into knots. Whether these loops are cosmic glitches or hidden features of reality, they remind us that the universe still has mysteries waiting to be unraveled. Time travel isn't just about bending physics, it's about untangling logic itself. The moment you consider going back in time, you're forced to wrestle with paradoxes, those mind-bending puzzles that threaten to unravel cause and effect. Take the grandfather paradox, the ultimate thought experiment. Suppose you built a time machine, traveled to the past, and accidentally prevented your grandparents from meeting. No grandparents, no parents, and ultimately no you. But if you don't exist, who went back in time to disrupt their meeting? The contradiction spirals endlessly, like a snake eating its own tail. This isn't just a plot hole in a sci-fi movie, it's a genuine headache for physicists. If time travel were possible, how could the universe enforce consistency? Some theories suggest nature might simply prevent such paradoxes, like an invisible hand nudging events to correct themselves. Maybe you'd slip on a banana peel at the critical moment, or your time machine would glitch something to keep history on track. Others propose parallel timelines, where every change splinters off a new reality, sidestepping the paradox entirely. Then there's the less grim but equally perplexing bootstrap paradox, where an object or piece of information loops endlessly with no origin. Imagine giving Shakespeare a copy of his own works before he wrote them, who really authored the plays. These puzzles aren't just fun brain teasers, they're clues about how time, causality, and the universe might really work under the hood. And until we crack them, time travel remains as much a philosophical labyrinth as a scientific one. Here's where physics throws us a fascinating lifeline in the paradox dilemma, the Novikov self-consistency principle. Picture this: you hop into a time machine determined to rewrite history, but no matter how hard you try, your actions only end up fulfilling what already happened. That's the core of Novikov's idea the universe has a built-in safety net. Proposed by Russian physicist Igor Novikov in the 1980s, the principle argues that any event causing a paradox simply can't happen. Time travel wouldn't be a free-for-all. Instead, it would bend to preserve consistency like a river flowing around rocks. Say you travel back to stop a historical disaster. Your attempt might fail in a way that subtly ensures the disaster still occurs, just as records show. It's not fate or destiny, it's physics enforcing rules. Think of it like a cosmic editor, trimming contradictions before they can unravel reality. This isn't just philosophy. Novikov's math suggests that probability itself might conspire to keep timelines intact. Quantum interactions, random fluctuations, even a misplaced footstep could nudge events toward the only outcome that doesn't break causality. Some scientists even tie this to quantum mechanics, where multiple possibilities collapse into one consistent history. So while time travel might let us witness the past, altering it could be like trying to stir concrete. Every move you make was already part of the mix. The universe, it seems, might hate paradoxes more than we love the idea of changing them. While wormholes and closed time-like curves stretch the fabric of space-time, quantum mechanics plays by an entirely different rulebook, one where particles defy logic and cause and effect aren't always set in stone. At the subatomic level, reality gets downright surreal. Take quantum entanglement, for instance, a phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, changing the state of one instantly affects the other, no matter how far apart they are. It's as if they're linked by an invisible thread, communicating faster than light could ever travel. Some physicists speculate that this eerie connection might hint at a deeper layer of reality where time isn't strictly linear. If entanglement can bridge vast distances in space, could it also thread moments together across time? That's where things get even weirder. Then there's retrocausality, the idea that the future might influence the past. In certain quantum experiments, particles seem to decide their behavior based on measurements made later. Imagine tossing a coin that only lands heads or tails after you've already called it. Experiments like the delayed choice quantum eraser suggest that at the quantum level, time might not flow in one fixed direction. Instead, it could be more like a two-way street, with future events subtly shaping the past. It's not quite hopping into a time machine, but it does challenge everything we thought we knew about cause and effect. The wild card in all this, quantum superposition, the same principle that lets Schrödinger's cat be both dead and alive until observed. If particles can exist in multiple states at once, could entire timelines branch out in parallel? Some interpretations of quantum mechanics suggest that every possible outcome does happen, just in separate universes. So instead of traveling back and altering your own past, you might simply shift into a new timeline where history played out differently. It's a cosmic version of what if, with reality splitting at every decision point like a choose-your-own-adventure book. Of course, scaling these quantum quirks up to human-sized time travel is a colossal leap. We're talking about phenomena that vanish the moment you try to pin them down, like grabbing smoke. But the tantalizing takeaway is this: at the deepest levels of reality, time might not be the rigid, one-way flow we experience. It could be far more fluid, more flexible, and who's to say we won't one day find a way to surf its waves? For now, quantum mechanics gives us a glimpse of a universe where the impossible might just be hiding in plain sight. Time dilation and time travel might sound like two sides of the same coin, but they play by very different rules. Picture an astronaut orbiting a black hole. While they experience just a few hours, decades pass for everyone back on Earth. That's time dilation in action, gravity or extreme speed stretching time like taffy, making clocks tick at different rates. It's real, measurable, and even affects your phone's GPS. But here's the key, it's still a one-way trip to the future. The astronaut can't loop back to relive those lost years. They're just riding time's natural current forward at a different pace. Actual time travel, though, that's about breaking free from time's arrow, entirely rewinding to the past or leapfrogging ahead on demand. Wormholes and closed time like curves tease this possibility, bending space-time into shortcuts or loops where cause and effect start to blur. Think of it like comparing a fast-forward button to rewinding the entire movie. One speeds up the plot, the other lets you rewrite the script. The confusion often comes from pop culture, where hovering near a black hole gets mashed up with hopping through time portals. But physics draws a firm line. Time dilation is nature's way of flexing time's elasticity, while time travel would require stitching cosmic holes in that fabric. Both are mind-bending, but only one lets you hypothetically meet your own grandfather before he's even a father, and that's a paradox no amount of time dilation can untangle. Black holes aren't just cosmic vacuum cleaners, they're nature's most extreme laboratories for bending time. At their edges, known as event horizons, gravity becomes so intense that not even light can escape. But what makes them truly mind-bending isn't just their pull, it's how they warp the very fabric of time. Picture this, if you could hover just outside a black hole's event horizon, time for you would slow to a crawl compared to the rest of the universe. A few minutes for you might be centuries everywhere else. It's like standing still while the world fast-forwards around you. Now dive deeper, past the point of no return. Inside a black hole, the rules we know break down completely. At its core lies the singularity, a point where gravity crushes matter into infinite density and space-time curves beyond recognition. Here, Einstein's equations suggest something wild. Time and space could swap roles. Instead of moving forward through time, you'd be dragged inexorably toward the singularity, as if time itself became a place you're falling into. Some theories even propose that singularities might punch through space-time, creating bridges to other universes or other times, though no one knows for sure, since the physics as we know it stops making sense. But here's the catch, crossing an event horizon is a one-way trip. Even if a black hole could twist time into a loop, sending you back to the past, you'd never be able to exit and tell the tale. The sheer tidal forces would stretch you into spaghetti long before you reach the singularity. Yet, the tantalizing possibility remains. What if some black holes, under the right conditions, could be gateways rather than dead ends? Rotating black holes, called Kerr black holes, might have ring-shaped singularities with just enough stability to avoid total collapse. The math hints that if you could navigate the chaotic interior, you might emerge somewhere or someone else. Of course, this is all speculative. No one's sending probes into a black hole anytime soon. But the fact that these cosmic monsters warp time so dramatically makes them irresistible to physicists and storytellers alike. Whether they're cosmic time machines or just nature's way of showing off, black holes remind us that the universe holds mysteries far stranger than fiction. And who knows, maybe one day we'll crack the code hidden in their infinite darkness. If black holes are the universe's ultimate one-way streets, white holes might just be their cosmic exit signs, theoretical counterparts spewing out everything black holes suck in. Picture a black hole's polar opposite, where nothing can enter, only escape. While black holes trap even light, white holes would violently repel it, acting like cosmic fountains gushing matter and energy into space. First proposed as mathematical curiosities in Einstein's equations, these enigmatic objects have never been observed, but they've captured scientists' imaginations for decades. Here's where it gets wild. Some theories suggest that a black hole and a white hole could be connected through a wormhole, like two ends of a cosmic tunnel. Matter falls into the black hole, rides the space-time shortcut, and bursts out the white hole potentially in another time or even another universe. It's the ultimate recycling system if it exists. But there's a catch. White holes violate the second law of thermodynamics, which says entropy, or disorder, always increases. A white hole would essentially reverse this, creating order from chaos, which physics typically forbids. Yet quantum gravity researchers aren't ready to dismiss them entirely. Some speculate that when a black hole dies, it might rebound as a white hole in a final explosive farewell. Others propose that the Big Bang itself could have been a primordial white hole, birthing our universe in a single burst of energy. Whether these ideas hold up or not, white holes remind us that the universe's rulebook might still have pages we haven't turned. And if they're out there lurking in the math or hiding in the cosmos, they could rewrite not just how we see space but time itself. When Hollywood needed a wormhole that could pass scientific muster, they turned to Kip Thorne, the physicist who helped turn interstellar travel from equations on a chalkboard into a visual masterpiece. Thorne didn't just consult on Interstellar, he co-wrote the film's treatment, insisting the science be as accurate as the drama was gripping. His calculations shaped the wormhole's iconic look, a shimmering sphere warping starlight into a halo, a visualization so precise it led to an actual scientific paper. But Thorne's influence runs far deeper than cinema. Back in the 1980s, he was already wrestling with a tantalizing question: could wormholes ever be traversable? His groundbreaking work laid the mathematical foundations, showing that with enough exotic matter, these space-time tunnels might stay open long enough to travel through. Of course, he also highlighted the hurdles: cosmic radiation, instability, the sheer energy required. But for the first time, wormholes weren't just sci-fi dreams. They were hypothetical engineering challenges. Thorne's collaboration with Carl Sagan on Contact further cemented his role as the bridge between hard science and cultural imagination. By blending rigorous physics with storytelling, he didn't just advance our understanding of space-time, he made us feel its possibilities. His legacy reminds us that the frontier of science isn't just about numbers, it's about daring to ask what if and letting the math lead the way. Imagine a machine where stepping inside could send you racing backward or forward through time. The Tipler cylinder is one such design, a colossal, ultra-dense tube spinning at nearly the speed of light. According to physicist Frank Tipler's calculations, its rotation would twist spacetime so violently that circling it could loop you back to your own past. Picture running laps around a cosmic whirlpool where time itself spirals inward. But here's the catch: building it would require materials denser than neutron stars and a way to spin them without tearing apart the laws of physics. Then there's the Alcubierre drive, a concept ripped straight from warp-speed sci-fi. Instead of moving through space, this theoretical craft would compress spacetime in front of it and expand it behind, surfing a wave of distorted reality. Mexican physicist Miguel Alcubierre showed in the 1990s that, mathematically, this could let you travel faster than light without actually breaking Einstein's speed limit. The twist: you'd also arrive before you left, effectively time traveling into the past. But powering this requires negative energy, a substance we've only glimpsed in quantum fluctuations smaller than atoms. Not all designs rely on cosmic megastructures. Some hinge on sheer cosmic luck, like stumbling upon a naturally occurring rotating black hole with a singularity shaped like a ring. If you could navigate its chaotic interior without being shredded, you might emerge in another era. Others play with cosmic strings, infinitely thin threads of leftover energy from the Big Bang that, if crossed just right, could warp spacetime into time loops. The common thread: every design dances on the edge of possibility, teasing time travel's potential while exposing the staggering gaps in our knowledge. Their less blueprints and more thought experiments remind us that the universe's rulebook might have loopholes we've yet to uncover. Until then, these machines remain locked in equations, waiting for a future genius or perhaps a time traveler to crack the code. Time travel might be hiding in the math, but turning those equations into reality would demand more energy than humanity has ever harnessed. Picture this: to pry open a wormhole wide enough for a single person, some calculations suggest you'd need the energy equivalent of several stars, converted into negative energy, no less. That's not just flipping a switch, it's rearranging the cosmos. Even a modest closed time-like curve could require a mass greater than Jupiter, spun to near light speeds. The numbers are so staggering, they border on absurd, yet they're what relativity demands. But here's the twist: nature might already be cheating. Quantum mechanics shows us that empty space isn't truly empty. It's a seething foam of virtual particles popping in and out of existence, sometimes with negative energy. Could we tap into that? In theory, yes, but scaling up from quantum flickers to a traversable wormhole is like trying to power a city with static electricity. The energy densities required are so extreme, they'd likely collapse any known structure long before stabilizing a time portal. Then there's the puzzle of efficiency. Even if we somehow gathered enough energy, controlling it would be another nightmare. Imagine trying to bottle a supernova the slightest misstep, and your wormhole might snap shut, explode, or worse, unleash unpredictable spacetime ripples. Some models propose workarounds like harnessing the spin of a black hole or threading cosmic strings, but these are hypothetical band-aids on a cosmic scale problem. Yet the challenge itself is revealing. The sheer energy barriers hint that if time travel is possible, the universe has built-in safeguards keeping it just out of reach, like a prize behind tempered glass. Maybe that's for the best. After all, if bending time were easy, we'd probably have met our future selves by now. Until then, the energy hurdle remains both a roadblock and a clue, a sign that the cosmos guards its secrets fiercely, even as it winks at us from the equations. Einstein's relativity gives us the bending of spacetime, and quantum mechanics reveals particles that defy time's arrow. But what happens when these two titans of physics collide? That's where quantum gravity steps in, the elusive theory that could stitch together the cosmos's biggest and smallest puzzles. Picture this: relativity paints spacetime as a smooth, flowing fabric, while quantum mechanics shows us a universe buzzing with tiny, discrete packets of energy. Reconciling these two visions isn't just about neat equations. It might hold the key to unlocking time travel in ways we've barely imagined. One leading candidate for this grand unification is string theory, which suggests that particles aren't dots but vibrating strings, and spacetime could harbor hidden dimensions curled up tighter than a coiled thread. If true, these extra dimensions might allow for shortcuts through spacetime wormholes stabilized not by exotic matter alone, but by the fundamental hum of these quantum strings. The math hints that under the right conditions, these structures could thread moments in time together like beads on a necklace. Then there's loop quantum gravity, which reimagines spacetime itself as a network of interconnected loops. Think of it as the universe's underlying pixelation. In this framework, time might not flow smoothly but tick in discrete steps like frames in a film. If these loops could twist or knot in just the right way, they might create pathways where time circles back on itself. It's a radical idea, but one that emerges naturally from the equations. The wild card in all this: quantum foam, a roiling sea of spacetime fluctuations at the smallest scales, where tiny wormholes might constantly blink in and out of existence. Some theories propose that harnessing these fleeting bubbles could provide gateways between different times, like stepping stones across a river of moments. The catch: we'd need technology fine enough to manipulate structures trillions of times smaller than atoms. While we're far from a unified theory, the quest for quantum gravity is more than academic. It's a search for the universe's hidden rulebook, one that might finally explain how time, that stubbornly persistent illusion, could become a dimension we navigate as freely as space. And if that day comes, the line between science and science fiction might vanish altogether. The idea of time travel might seem confined to chalkboards and thought experiments, but what if nature has already dropped us clues in real-world labs? Over the years, scientists have stumbled onto phenomena that make even seasoned physicists raise an eyebrow. Take the notorious neutrino anomaly from 2011, when particles called neutrinos appeared to break Einstein's ultimate speed limit. In experiments at CERN, these ghostly particles seem to arrive 60 nanoseconds faster than light should allow, a result that, if true, would have shattered our understanding of causality. The implications were dizzying. Could neutrinos be slipping through microscopic wrinkles in spacetime, taking shortcuts that effectively sent them backward in time? The frenzy lasted months until tighter measurements revealed a loose cable in the equipment had skewed the data. But for a brief moment, the universe flirted with rewriting its own rules. Then there's quantum entanglement's eerie defiance of time's arrow. In labs worldwide, entangled particles react to each other's state instantaneously, no matter the distance. While this doesn't quite break causality, you can't use it to send messages faster than light. It does suggest that at the quantum level, time might not be the rigid one-way street we experience. Some interpretations argue these particles are coordinating across time itself, with future measurements influencing past states. It's as if the universe keeps a tab open between moments, editing the script in real time. Even black holes, those cosmic gatekeepers of gravity, might be leaking hints. Stephen Hawking's work on Hawking radiation suggests information isn't truly lost when matter falls into a black hole. It's scrambled and slowly emitted back out over eons. Some theorists propose this process could create subtle time-reversed effects near the event horizon, like echoes from the future. While we're far from definitive proof, these oddities remind us that nature's playbook might have pages we've yet to turn. Perhaps the most tantalizing glimmers come from quantum mechanics itself. Experiments with photons have shown particles behaving as if they're looping back in time to choose their paths retroactively. In one study, photons passing through a maze of mirrors seemed to adjust their routes based on measurements made after they'd already traveled, a head-scratching effect that nudges us to question whether time's arrow is as fixed as we think. None of this amounts to a time machine in a garage, but collectively, it paints a picture of a universe far more flexible than we once imagined. From misbehaving neutrinos to entangled particles whispering across time, these anomalies are like cosmic breadcrumbs, leading us toward questions we're only beginning to frame. And sometimes the most groundbreaking discoveries start with a flicker of data that refuses to fit the mold. If today's universe seems strict about time's one-way flow, the early cosmos might have played by different rules. Picture the first moments after the Big Bang, a seething, hyperactive landscape where spacetime itself was still taking shape. In that primordial chaos, extreme energy densities and temperatures could have stretched reality in ways we can barely imagine. Some theories suggest these conditions were so wild, they might have birthed wormholes or closed time like curves, naturally like cosmic wrinkles frozen into the fabric of creation. Think of it like bubbles forming in boiling water. In the early universe's hot, dense soup, quantum fluctuations could have briefly warped spacetime into tunnels or loops before stability set in. If even a few of these structures survived as the universe expanded and cooled, they'd be relics of a time when physics was far more flexible. The catch: finding evidence, these ancient shortcuts would be incredibly fragile, possibly hidden in the cosmic background radiation, or disguised as black holes we've already detected without realizing their deeper secrets. The math gets even more intriguing when you consider inflation, the theory that the universe expanded exponentially in its first fraction of a second. If spacetime stretched that violently, could it have twisted into knots or bridges? Some models hint that microscopic wormholes, far smaller than an atom, might have been woven into the universe's structure during this explosive growth spurt. Over billions of years, gravitational forces could have stretched some of these tiny tunnels into larger, navigable paths, assuming they didn't collapse first. Then there's the question of cosmic strings, hypothetical defects in spacetime left over from the early universe. These ultra-thin, unimaginably dense threads could warp spacetime around them like a guitar string warps the air when plucked. If two strings looped or crossed in just the right way, they might have formed closed time-like curves, natural time loops embedded in the cosmos before stars or galaxies even existed. Of course, all this remains speculation wrapped in equations, but the tantalizing idea remains: if time travel is possible, the universe might have built the first prototypes itself. The challenge isn't just proving they existed, it's figuring out whether any of them survived long enough for us to stumble upon them. And if we ever do, it'd mean the cosmos handed us keys to time itself, forged in its own fiery birth. What if you could stop a war before it began, or erase a mistake before it ever happened? Time travel isn't just a physics problem, it's a moral minefield. The moment we entertain the idea of changing history, we're forced to confront questions that philosophers have wrestled with for centuries. Who gets to decide which events are rewritten? Would fixing one tragedy unintentionally unleash another? The power to alter time isn't just about bending space-time, it's about playing with consequences we can't fully predict. Take the butterfly effect, a concept from chaos theory where tiny changes snowball into massive outcomes. If you traveled back to prevent a single assassination, could you inadvertently trigger a worse conflict? History is a fragile web of cause and effect. Tug one thread, and the whole tapestry might unravel. Even with the best intentions, meddling with the past could erase entire lineages, cultures, or technological advancements, all because someone thought they knew better. Then there's the question of privilege. If time travel became reality, who would control it? Governments, corporations, the ultra-wealthy. The potential for abuse is staggering. Imagine a world where the powerful rewrite history to cement their dominance, while the rest of us live with the fallout. And what about personal responsibility? If you could undo every regret, would life lose its meaning? Growth often comes from facing consequences, not erasing them. But maybe the most haunting dilemma is one of identity. If you change the past, do you erase the person you became because of it? The you who learned from failure, who grew through hardship, would they still exist, or would they vanish into a timeline that never was? Time travel doesn't just risk paradoxes, it risks losing the very essence of what makes us human. Of course, some argue that tampering with time might be impossible, no matter the technology. The Novikov self-consistency principle suggests the universe could force events to align, making any changes you attempt part of what always happened. But even then, the ethical weight remains. If you can't alter the past, does witnessing it without intervening make you complicit? The deeper we dig, the clearer it becomes. Time travel isn't just about how we do it, but whether we should. And that's a question no equation can answer. If time travel were possible, would every choice you make already be set in stone? This isn't just a sci-fi plot twist, it's a deep dive into one of philosophy's oldest debates: free will versus determinism. On one side, there's the deterministic view, the idea that every event, from the motion of planets to the thoughts in your head, is the inevitable result of prior causes. In this universe, time travel wouldn't change anything. You'd simply be fulfilling what was always meant to happen. Your decisions would just be echoes of a script written long before you arrived. Picture a record playing the same song no matter how many times you drop the needle. But then there's the indeterministic perspective, the belief that randomness and genuine choice exist in the fabric of reality. Quantum mechanics already shows us particles behaving unpredictably, so why not human actions? In this version of the universe, time travel could introduce true branching paths. You might step into the past with free will intact, only to watch your choices ripple outward in ways no one, not even the laws of physics, could fully predict. It's less like following a script and more like rewriting it with every move. The tension between these views forces us to ask, if time travelers could alter events, would their actions be truly theirs, or just the universe correcting itself? Philosopher John Locke once pondered whether a man placed in a locked room, unaware the door's locked, still has the freedom to choose not to leave. Time travel might put us in that same room, making choices we think are free until we realize history's walls were always there. Yet some theories suggest a middle ground. Compatibilism argues free will and determinism can coexist, that even in a predetermined world, our choices matter because they're part of the causal chain. In this light, a time traveler's decisions might shape events precisely because they were always meant to. No paradoxes, no fixed fate, just a universe flexible enough to weave new threads into its own timeline. Whether time travel would shackle us to destiny or set us loose in a garden of forking paths hinges on questions science hasn't answered yet. But one thing's certain: the moment we unlock time's doors, we won't just be testing physics. We'll be probing the very nature of choice itself. What if every time you made a choice, the universe split in two? The idea might sound like science fiction, but it's one of the most compelling ways physics could dodge the headache of time travel paradoxes. Welcome to the multiverse. Imagine stepping into a time machine, traveling back to prevent a disaster and succeeding. In a single timeline universe, that success would erase the future you came from, including your reason for going back in the first place. But in a multiverse, your actions wouldn't rewrite history. They'd just branch off a brand new timeline, untouched by the one you left behind. This isn't just creative storytelling, it's rooted in real science. The many worlds interpretation of quantum mechanics suggests that every possible outcome of every event actually happens, each in its own parallel universe. Flip a coin and in one reality it lands heads, in another tails. Now scale that up to time travel. Go back and change something major, and instead of creating a paradox, you'd simply spin off a new, self-consistent timeline where both versions of history exist side by side. Your original past remains intact, unaltered, while the new one unfolds with your edits in place. Think of it like a choose-your-own adventure book where every decision forks the story. Turn left instead of right, and the narrative splits. One path leads to danger, the other to safety. Both stories continue independently, never colliding. That's the multiverse solution in a nutshell. No grandfather paradoxes, no bootstrap headaches, just infinite alternate realities where every possible past, present, and future plays out simultaneously. But here's the catch: while this neatly sidesteps logical inconsistencies, it raises its own profound questions. If infinite versions of you exist across timelines, which one is the real you? Could you ever return to your original universe, or would you forever be hopping between branches? And if every choice spawns new worlds, does accountability lose meaning when mistakes can just be abandoned in another timeline? The beauty of the multiverse approach is that it turns time travel from a cosmic logic puzzle into a matter of navigation. Instead of worrying about unraveling reality, you're surfing a vast ocean of possibilities, each wave a new version of history, each ripple a choice you didn't make. Whether this is how our universe actually works remains unknown, but it's a dazzling reminder that the answers to time's mysteries might not lie in bending a single timeline, but in embracing the infinite. What if breaking the universe's speed limit is the secret to unlocking time itself? Einstein's theory of relativity insists nothing can outpace light, but some theories suggest loopholes that might just bend that rule. Enter tachyons, hypothetical particles that only exist faster than light. Unlike ordinary matter, these speedsters wouldn't slow down to light speed. They'd accelerate the further you tried to break them. And here's the wild part: if tachyons are real, they'd experience time backward. From their perspective, they'd move from the future to the past, like rewinding a film reel. That's not just fast travel, it's a built-in time machine. Of course, no one's ever detected a tachyon, and their existence would upend physics as we know it. But the tantalizing possibility remains. If nature allows even one exception to light speed, time travel might be closer than we think. Then there's the warp drive, a concept that cheats the speed limit without technically breaking it. Instead of moving through space, this theoretical engine compresses space-time ahead and stretches it behind, riding a wave of distorted reality. Picture a surfer on a tidal wave. The water itself isn't moving the surfer forward, the wave is. In this case, the wave is space-time bending around the ship. The kicker, Einstein's equations allow it, but the energy required is staggering. Think entire planets converted into pure fuel. The real mind-bender, though, is what happens if you arrive before you leave. At superluminal speeds, causality gets tangled. You might reach your destination so fast your departure becomes the future, effectively jumping backward in time. But here's the catch: both ideas flirt with paradoxes. If faster-than-light travel enables time loops, could a message from the future alter the past that created it? Quantum physics offers fuzzy workarounds like parallel timelines or self-correcting events. Yet the deeper truth is this: the universe seems to guard causality fiercely, even as it winks at us with theoretical backdoors. Whether through tachyons, warp bubbles, or some yet undiscovered phenomenon, the link between speed and time is undeniable. After all, if you can outrun light, you might just outrun time itself. String theory paints a picture of the universe that's far stranger than anything we experience in our everyday lives. It suggests that reality isn't just the 3 dimensions of space and one of time we're familiar with. There could be up to 10 or 11 dimensions, all curled up and hidden from view. These extra dimensions aren't just theoretical fluff. They might hold the key to unlocking time travel's greatest mysteries. Imagine space-time not as a flat sheet, but as a multidimensional tapestry woven with threads we can't yet see. In this richer, more complex fabric, the rules could bend in ways that make wormholes or time loops not just possible, but inevitable. Take the idea of a Calabi-Yau manifold, a tiny, 6-dimensional shape that string theory predicts could exist at every point in space. These intricate structures are like the universe's hidden origami, folding in ways that could allow shortcuts through space-time. If one of these folds were to connect 2 distant points in time, we might not need exotic matter to stabilize a wormhole. The extra dimensions could do the heavy lifting. Think of it like a tunnel dug through the side of a mountain instead of going over it. The extra dimensions provide a natural geometry that sidesteps the usual obstacles. And then there's the brain world scenario, where our entire universe is just a 4-dimensional brain floating in a higher dimensional space. If other brains exist parallel to ours, collisions or gravitational interactions between them might warp space-time in extreme ways, perhaps even creating temporary bridges between different eras. Picture 2 sheets of paper drifting close together, and for a fleeting moment their surfaces touch. Could that contact point be a portal not just to another place but to another time? String theory doesn't just add dimensions, it redefines how gravity and quantum mechanics interact. In this framework, the vibrational patterns of tiny strings could determine everything from particle masses to the curvature of spacetime itself. Some models even suggest that certain vibrations might resonate across time, like echoes bouncing between the walls of higher dimensions. If that's true, then time travel wouldn't require a massive machine, just the right kind of quantum tuning fork to pluck the strings of reality in just the right way. Of course, all this remains speculative. We don't yet have experiments to confirm extra dimensions, let alone manipulate them. But the mathematics hints at possibilities too compelling to ignore, that hidden within the geometry of the cosmos, the doors to time itself might already be waiting. And if string theory holds even a fraction of its promise, our universe could be far more fluid, more malleable than we ever imagined. The question isn't just whether we can travel through time, it's whether we're brave enough to explore the dimensions where time might not even flow the way we think it does. Even if wormholes exist, spotting them in the vast emptiness of space would be like finding a single flickering candle in a hurricane. The problem isn't just their size or distance, it's that they might not look anything like the glowing portals we see in movies. A real traversable wormhole could be nearly invisible, bending light so subtly that it blends into the cosmic background. Without some telltale signature like unusual gravitational lensing or bizarre particle movements nearby, it could hide in plain sight, disguised as just another patch of darkness. Then there's the issue of scale. Some theories suggest stable wormholes might only exist at microscopic levels, smaller than atoms, popping in and out of existence before we could even aim a telescope. Others propose they'd need the mass of entire stars to stay open, but something that massive would likely collapse into a black hole long before we could study it. Either way, our current tools aren't built to scan for something that could be as fleeting as a quantum fluctuation or as elusive as a shadow. Even if we got lucky and spotted a candidate proving it's a wormhole, and not just a black hole or a dense star, would take precision we don't yet have. Black holes distort light and warp spacetime too, so how could we tell the difference? Some scientists suggest looking for unusual radiation patterns or gravitational echoes that don't match known objects. Others propose sending probes, but with the nearest potential wormhole likely thousands of light years away. That's not exactly a quick experiment. And here's the ultimate irony. If wormholes do connect distant points in spacetime, the signals we'd use to detect them might be scrambled beyond recognition by the journey itself. Light or radio waves passing through could emerge stretched, redshifted, or fragmented, like a message sent through a broken telephone. Until we develop technology sensitive enough to decode those cosmic hiccups, wormholes will stay in the realm of equations and dreams. Yet the search isn't hopeless. New telescopes like the James Webb or future gravitational wave detectors might catch anomalies that older instruments missed. Every unexplained ripple in spacetime, every odd flicker of light, could be a clue not just to wormholes, but to the hidden architecture of reality itself. The universe loves secrecy, but it always leaves traces. We just have to learn how to read them. Imagine waking up in a world where artificial intelligence has cracked the code of spacetime. Picture quantum supercomputers running simulations so precise, they uncover hidden patterns in the fabric of reality, patterns that hint at how to stabilize a wormhole or engineer a closed time-like curve. This isn't just fantasy, it's the cutting edge of what's being explored in labs today. AI could become our ultimate cosmic detective, sifting through petabytes of astronomical data to spot anomalies that human eyes might miss. Tiny gravitational quirks or radiation signatures that point to natural time loop structures hidden in deep space. Next, consider the potential of quantum technologies. We're already seeing early prototypes of quantum computers that manipulate particles in ways classical physics can't explain. In the coming decades, scaled-up versions might simulate entire sections of spacetime, letting us test hypothetical time machines digitally before attempting to build them. Think of it as a cosmic sandbox where we can tweak the rules of relativity and quantum mechanics, running endless what-if scenarios until we stumble upon a configuration that bends time without breaking physics. Then there's the wild card, fusion energy. If we ever harness the power of stars here on Earth, the sheer energy output could fuel the kind of exotic matter production needed to prop open a wormhole. Imagine fusion reactors generating not just clean electricity, but the negative energy densities required to stitch together points in time. Suddenly, the astronomical energy demands we mentioned earlier start looking a little less impossible. But the real game changer might lie in large-scale physics experiments beyond even the Large Hadron Collider. Future colliders operating at energies 100 times higher could recreate conditions from the early universe, perhaps even spawning microscopic wormholes or spacetime loops in controlled settings. Detecting these fleeting phenomena would prove that time travel isn't just math on a chalkboard, but a tangible, if elusive, feature of our universe. And let's not forget material science. The discovery of room temperature superconductors or ultra-dense metamaterials could revolutionize how we manipulate gravitational fields. If we engineer substances that mimic the extreme properties of neutron stars or cosmic strings, we might finally bend spacetime with precision, turning theoretical blueprints into tangible machinery. Of course, these advancements won't happen overnight. They'll emerge from decades of collaboration between physicists, engineers, and even philosophers wrestling with the ethics and implications. But the trajectory is clear. The tools we're building today, AI, quantum tech, fusion, aren't just changing our world. They're preparing us to step into a far stranger one, where time itself becomes a dimension we can navigate. The future of time travel isn't just about dreaming, it's about building, and the next breakthrough might be closer than we think. Science fiction loves to dress up time travel with flashing lights, whirring machines, and dramatic leaps through swirling vortexes. But strip away the Hollywood spectacle, and you'll find the real science is far stranger and often more subtle. Take the classic time machine trope, a sleek device with levers and glowing dials that catapults characters across centuries. In reality, if time travel were possible, it wouldn't involve a handheld gadget. It'd require bending spacetime itself, harnessing cosmic forces like gravity or exotic matter. No DeLoreans, no blue police boxes, just the raw architecture of the universe. Films often treat time like a train track, where hopping backward just means reversing direction. But physicists see time as more like a river, one that can speed up, slow down, or even loop back on itself under extreme conditions. Think of Interstellar's portrayal of time dilation near Gargantua, where hours on the water planet equal years elsewhere. That part surprisingly accurate, but when characters survive inside a black hole singularity, chatting in a 5-dimensional bookshelf, that's where science taps out and storytelling takes over. Singularities aren't scribbled on voids, they're points of infinite density where physics as we know it collapses. Then there's the messy business of paradoxes. Movies love the drama of altering history, saving a loved one, preventing a war, but often ignore the logical landmines. Real theories like Novikov's self-consistency principle suggest the universe wouldn't allow contradictions. You couldn't erase your own existence any more than you could toss a rock upstream and change the river's source. Even the multiverse theory, where every choice spawns new timelines, gets oversimplified. Sci-fi shows parallel worlds as neat, visitable alternates, but in reality, branching universes would be inaccessible, their histories diverging at the quantum level. Perhaps the biggest myth that time travel would be easy. Blockbusters make it seem like a jaunt to the past is just an equation or a flux capacitor away. The truth, it'd demand energy scales we can't fathom and materials that might not exist. Wormholes, if they're out there, wouldn't glow ominously, they'd be invisible, fragile, and possibly microscopic. And forget leaping into the future with a push of a button. You'd need to orbit a black hole for decades or accelerate to near-light speeds, leaving everyone you know behind. Yet for all its inaccuracies, sci-fi deserves credit. It's inspired generations to ask, what if? And sometimes the line between fiction and prediction blurs. Kip Thorne's work on Interstellar led to real scientific insights about black hole visualization. The genre's role isn't just to entertain, it's to stretch our imagination until science catches up. Because who knows, today's cinematic fantasy might one day be tomorrow's lab experiment. After all, the universe has surprised us before. Time travel has been twisted by pop culture into something far simpler and far more glamorous than the science suggests. One of the biggest myths that hopping through time would be as easy as flipping a switch. Movies show characters stepping into sleek machines and vanishing into the past or future in an instant. But here's the reality. Even if wormholes or closed time-like curves exist, traversing them wouldn't be a smooth ride. The gravitational forces alone could tear you apart before you cross the threshold, and stabilizing a time portal would require energy and materials we can't even fathom yet. Then there's the persistent idea that time travel must already be happening in secret. that governments or shadowy organizations are hiding the technology. It's a fun premise for conspiracy theories, but let's break it down. If time travel were possible today, wouldn't we see evidence like unexplained objects in historical records or sudden leaps in technology? Even the slightest interference in the past could ripple forward in obvious ways, and forget about covering it up. Something as world-altering as time travel would be impossible to contain. The truth is, if anyone had cracked it, we'd know. Another common misunderstanding is that traveling through time means arriving exactly where and when you intend. In reality, space-time isn't a static grid, it's a dynamic, shifting fabric. A wormhole's exit point could drift due to gravitational waves or cosmic expansion, meaning you might miss your target century or even your target planet by a wide margin. Precision time travel would require navigating forces we're only beginning to understand. And don't get me started on the idea that you could casually change history without consequences. The grandfather paradox gets all the attention, but there are subtler issues. Even a minor tweak like moving a single pebble in ancient times could snowball into catastrophic shifts over millennia. The universe isn't a simulation where you can reload a save file. Every action could have irreversible, unintended effects, perhaps the most insidious myth. That time travelers would look or act like ordinary people, blending seamlessly into different eras. The reality, they'd stick out immediately. Language, technology, even microbes, every detail of daily life changes dramatically across centuries. A modern human in medieval Europe wouldn't just sound strange. They'd risk introducing pathogens that could rewrite history unintentionally. The takeaway: time travel, if it's ever possible, won't resemble the Hollywood version. It'll be messy, unpredictable, and bound by laws of physics we're still uncovering. But that's what makes it so fascinating, not as a magic trick, but as one of the universe's deepest puzzles waiting to be solved. So where does all this leave us in our quest to unlock time travel? We've explored how wormholes could act as cosmic shortcuts, bending space-time to connect distant moments, if only we could find or create one stable enough to traverse. We've unraveled the mind-bending potential of closed time like curves, those loops in the fabric of reality where cause and effect start to blur. The math says these phenomena could exist, but the hurdles are astronomical, from the need for exotic matter we've barely glimpsed to energy requirements that dwarf our planet's entire output. Yet the most fascinating part isn't just the obstacles, it's how these ideas stretch our understanding of the universe itself. Time might not be the rigid, one-way flow we experience, but something far more fluid, woven into dimensions we can't yet perceive. Whether through quantum entanglements, eerie connections, or hidden geometries in string theory, nature keeps hinting that time's secrets are deeper than we imagined. As we stand on the edge of these possibilities, here's a question to leave you with. If you could ask one question to a future version of humanity, or even your own future self, what would it be? Drop your answers below, and who knows, maybe someday, against all odds, we'll find a way to send that message across time itself. Until then, keep looking up. The universe still has plenty of surprises in store.